Okay, I want to start today by showing you the penny in the cup trick. So I have a penny in the bottom of this cup. You can see it there. I'm going to move the cup so that we can barely not see the penny. So the penny is now covered up exactly by the cup. Without moving the camera, I'm going to fill this thing with some water and let's see what happens. We can now see the penny. All right, today we're going to start an investigation to kind of determine how this actually worked. What is the light doing as it exits the cup in order to get to your eye? Before there was water in there, the light was going barely from the edge of the penny, or if right off of the penny, straight out the cup. But something happened when I added the water. We're going to do an investigation today to see if we can't figure out how light actually bends when it enters new materials. Okay, normally you can't see a laser beam when it's in the air. You can only see when it bounces off of something. So what I can do is I can actually put some chalk dust. I have some chalk here. Put some chalk dust in the air so that when I shine the laser beam, you can actually see it through the air because it has something to reflect off of. I'm going to do that in the air. In the water, as we put this in water, I have some baking soda I'm going to put in the water just to kind of make it a little more cloudy, I guess. So that we can see what's going on in there. So here we go. So some chalk dust above and baking soda in, and let's see what happens. Now you'll notice the beam is coming into the water and then it changes direction. It actually bends. Let's see if I can get some more chalk dust up here. There we go. So the beam is entering the water. Instead of going straight, it bends. Let's see if we can't take some data. Okay, the lab setup looks a lot like this. What I have here is I have a laser pointer, I have a pencil, I have some graph paper, and I have a half-moon dish with a little line in it. I filled the half-moon dish almost full with water. I didn't want to put too much so I didn't spill anything. I put the line on the sheet of paper where this dish is located in case I move it. And I'll try to put this line directly on there so that I know that this is kind of the center in case something gets bumped. So what we're going to do is we are actually going to shine the laser at an angle through this dish. Okay? So this is kind of more difficult to do with one person, but I think I can handle it. So the first thing I'm going to do is I'm just going to keep my hand at this angle right here. And you can see that the laser is going through the dish. So I'm going to start by drawing the laser as it comes in, because I'm going to want to measure that angle. Then, as it goes through, I can draw where the laser comes out. So now I have the laser going in and the laser coming out. I'm then going to adjust my angle, still hitting the same spot here on the dish. I'm going to draw the angle going in. We'll call this one A. We'll call this one B. This one's A. And then, oh no, that's bad. Okay, there's the angle going in. And the angle coming out is right there. So, I have these things. And so what I can do is I can measure angles going in and angles going out. So technically, we always measure these angles from a normal line, or a line perpendicular to the surface. So this is the normal. The word normal means perpendicular to the surface, similar to the normal force. So I have an angle here for A, and I have an angle here for B. On the other side, straight edge here. On the other side, that's B, and this is A. So from the normal line again, this is A and this is B. And you can see that they actually did bend. B came in like this, then it bent like this. It did not go straight through, it bent. A didn't seem to bend as much, but it did bend a little. It almost looks like A should be right there. So we can actually measure some angles for these different motions of light through different media. All right, so let's talk about how this works. I want to look at when light bends entering a new material. I want you to be able to predict which way is it going to bend. Often we say, does it bend towards the normal or away from the normal? And I also want you to be able to predict mathematically what that angle of refraction is going to be. When light enters a new material, it bends. It does this because it changes its speed. We said earlier on that the only thing that changes the speed of a wave is a change in medium. We know that light in a vacuum travels at 3 times 10 to the 8th meters per second. In air, it actually travels a little bit slower. In glass, it travels a little bit slower. In water, it travels a little bit slower. So in different materials, light actually goes different rates. That's because, just like we did with slinkies, any change in medium actually changes the speed of the wave. So why does it bend? Well, one way that I always think about when I think about how it bends is I always think about a tractor. So if I want to predict if it's going to bend towards or away from the normal, I want to think about a tractor. So let's imagine that I've got 2 surfaces. Okay? I have, the road that a tractor goes on, and then I have maybe some mud. Okay? And in Iowa, we get this a lot. We see tractors on the highway, and then they enter the field. Now, the way this works is the tractor is going to enter the field at an angle like this. And it's going to bend when it enters. Now, I'm going to draw a normal line on here so that we can get an idea of what this is going to look like. I want to know, is it going to bend down, which would be towards the normal, or is it going to bend out, which is away from the normal? I have an angle right here, which we would call the angle of incidence leading into the boundary, and then the angle of refraction is going to be down here. So, let's think about this. On a road, a tractor travels fast. In the mud, it travels slow. So, here's how a tractor works. A tractor has 4 wheels. It has 2 wheels in the front, 2 wheels in the back. So let's think about what's happening here. As this tractor is coming in, it's going to hit the boundary. So it has 2 wheels in the front here. It's got a wheel here and a wheel here, a wheel here and a wheel here. Which wheel hits the boundary first? Well, it's going to be this bottom right-hand wheel. And when that hits the boundary, it's actually going to slow down, which actually brings the top part of the tractor turned. So this one slows down. The top part's still going fast, so this actually bends, call it angle of refraction, towards the normal. If you're going from fast to slow, it bends towards the normal. And you can think about tractors in order to figure this out. So that's all great and everything for tractors, but what about light? How do I know if light's going to go faster or slower in given materials? Well, we have a number that we link to the speed of light in given materials. Now, if you remember, the speed of light is 3 times 10 to the 8th meters per second. In water, it might be something like, 2.3 times 10 to the 8th. I made that up. I don't know if it's true. But it's going to be a little bit slower. But still, these are really big numbers. So if we're going to use these numbers to mathematically figure out how this thing's going to bend, I don't want to use such big numbers. So they actually came up with a different number called the index of refraction. The index of refraction is given the variable n. And an n, lowercase n, is denoted as index of refraction. And what it is it's the ratio of the speed of light in that material to the speed of light in a vacuum. So what you do is you do n is equal to c over v. C being 3 times 10 to the 8th, the speed of light in a vacuum. V being the speed of light in that material. Which means this speed of light in a vacuum is always going to be a little bit bigger than this because nothing can go faster than the speed of light. So, some indexes of refraction that you might be interested in. So the index of refraction for a vacuum would be c over c, which is 1. So the index of refraction in a vacuum is 1. The index of refraction in air is like 1.001. It's almost the same, which means light almost goes just as fast in a vacuum as it does in air, or just as much in air as it does in a vacuum. The index of refraction for water is 1.33, meaning that it does slow down when it hits water. It slows down more in water than it does in air because it has a higher index of refraction. The index of refraction for glass really depends on the type of glass, but a lot of times they're around 1.5. Diamond is like 2.42, meaning the light actually really slows down in a diamond, which is actually part of what makes it sparkle and puts the colors inside a diamond. So the index of refraction is the ratio of the speed of light to the actual speed of light in the material. And we're going to use that in order to calculate the angle that it's going to refract at. So using tractor wheels, we can try to predict if it's going to bend towards or away from the normal, depending upon which wheel speeds up or slows down. That's really qualitative. To quantitatively do this, we got to go into Mr. Snell's Law, named after Mr. Snell. So Snell figured out that this ratio of the indexes of refraction actually has to do with the ratio of the angles that are in the situation. You actually probably figured this out with your half-moon dishes. The light bent as it hit that half-moon dish. Incidentally, how come it didn't bend when it went from the water back out to the air? Well, that's interesting. If you look at that half-moon dish, they're shaped as a half-moon for this purpose exactly. We are hitting the middle here. So the beam of light comes in, and then the beam of light goes out like this. And it did not bend when it hit the edge of this half-moon dish. And the reason for that is because just think about tractor wheels, as it came out, since it's going from the center of the circle to the outside, both wheels hit at the same time. If both wheels hit at the same time, it's not going to bend. So in this case, the reason we did a half-moon dish is so that we only have one bending right here at the beginning. This is also true if you're looking straight down on something, it's not going to bend either because the angle of incidence is 0. So in this case, we have an angle here with a index of refraction on the top. This might be air, and this down here might be water like we did with the aquarium. So you have an angle of refraction, or angle 2, and N2. When we put those in the equation, N1 times the sine of theta 1 is equal to N2 times the sine of theta 2. And we can use this to actually solve problems where we can predict things. If you know the two materials, you know the indexes of refraction, and you know one of these angles, you should be able to solve for the other. Go ahead and work through your worksheet. Tomorrow, we're going to talk about a special situation that deals with this. Thank you so much for watching. If you like science and you like this video, feel free to like this video below and subscribe for future updates.